Assalamu alaikum, everyone, and very good morning, and welcome to today's session. So, in the last class, we actually started the topic of excitation system modeling, and we went through the types actually. So, we started from the basic definition of the excitation system, and to be specific, this excitation system is actually associated, the modeling is associated with the conventional synchronous machine. Okay. So then we discussed the necessity of an excitation system, the functions of the excitation system, where the function, there are three major functions if we want to categorize them. First block is the control function, then there are some limiting functions, and finally there are some protective functions. And associated with the limiting functions, there is a specific curve. There is a synchronous machine capability curve, and in that curve we might find the associated limits for the synchronous machine operation, or the safe zone of operation to be specific. Then this schematic of the excitation system was taken into consideration, where we discussed in brief about each of the blocks, like the exciter block, the voltage regulator block, the stabilizer block, and the transducer and load compensator, and as well the limiters and protective circuits. Then we talked about the three major categories for the excitation system, or the exciter itself, which is actually a part of the excitation system. So if I talk about the excitation system, we actually talk about the whole block diagram over here and their connectivity. However, when we talk about the exciter, then we are actually only focusing on this middle block, okay, which could be DC, AC, or static. So then we went through the schematic diagrams and a brief operating principle of these three categories of exciter model, like the DC exciter model, where we have the rotating amplifier used for controlling the field current to the exciter itself. And of course, the voltage regulator is there, which takes the feedback from the terminal of the power system, as well as the power for the reference set point. It takes the value from the DC exciter output. And then the comparison is done, and accordingly, the field excitation of the amplidyne is varied, which actually ultimately varies the field current of the DC exciter. And thus, the field of the main generator is being controlled. Then we moved on to the AC exciter, where we might have different variants, like, of course, there will be a rectifier, because this is AC exciter. Now we generally use the AC machine for the excitation purpose. But because in our actual generator, that is the main generator, the field itself is fed by DC. So once we are generating AC from the exciter, so we have to take help of the rectification process. And the rectification in the exciter itself, there could be controlled rectification or uncontrolled rectification. The rectifiers could be stationary, or even it could be rotating. So based on that, there could be different variants for that. And we took actually three examples. One was the field control alternator rectifier excitation system, where we had both provisions for DC voltage regulation and AC voltage regulation. The DC voltage regulation was, of course, the manual control, and the primary control, or the main control, has to be provided by the AC voltage regulator. So this has priority over the DC voltage regulator. If somehow this fails to provide the necessary control, then DC voltage regulator should come into action. And of course, they are mutually exclusive. Okay, so if this path is closed, then this should be open, and vice versa. And here we saw that, well, the control is actually provided in the field circuit of the AC exciter. Okay, so this is the control, and this is the rectification, basically the intermediate rectification required for converting the AC here to the DC, which is fed ultimately to the field circuit. The second example was alternator supplied control rectifier rectification system. And here we have dual control. One is the exciter regulator, which is controlling the AC exciter, and another one is the rectifier of the main field of the main generator. Okay. And here again, we have both provisions for DC and AC. The third type was the brushless type, where there were several structures which were rotating actually. The field of the pilot exciter was rotating, which was permanent magnet type. Then we had the armature and the uncontrolled rectifier part for the main generator field excitation. And this was the main field. So because this is rotating, so you don't have the provision actually to access the DC voltage information. So you can only access the information of the AC terminal voltage, which is available at the terminal of the main generator. And that is fed to the AC voltage regulator, which is actually controlling the field of the AC exciter. Okay, field of the AC exciter is controlled. Then we talked about the AC exciter, where actually that instead of all those rotating parts that we saw earlier, like in this case, this was rotating, this was rotating. So there are many rotating parts in the excitation system. However, in the static system, we simply use a transformer, and the signal at the from the terminal of the main generator, voltage signal is fed back to the transformer input, and the output is fed to the controlled rectifier. And the control rectifier pulse gates are actually generated from either from the DC voltage regulator or from the AC voltage regulator. So because there are no rotating parts in the excitation blocks, we call it static excitation system. And this is a great example of that. Actually, there are other variants for this, okay, which you might find in the book of Prabha Kundur in the excitation system chapter. And the example here, the name is potential source controlled rectifier excitation system. And then we talked about the terminal voltage transducer, the voltage regulator, and some other elements which are integral part of the overall excitation system. That is load compensator, the stabilizer, and the limiters and protective circuits. So what we'll do today, we will start with the modeling of the excitation system, and specifically the modeling varies a little bit. Of course, there are different types, like there are DC, AC, and static, but we are not going to go through all those details, okay, separately for each of them. Or rather, I will take one example to start with, that is separately excited DC exciter. This is the first example given in the book, and the remaining is depending on your interest, you can go through that. Okay, but I'm only going to discuss the first one. So in the separately excited DC exciter, we have the armature, and this is simply a DC machine. So you can even call it a separately excited DC generator, nothing else. So in the separate excited DC generator, what do we have actually in the field block? And the first thing is there is no connection between the field circuit and the armature circuit. There are no electrical connection. Okay. So the field is fed by an external source. So let's say the voltage source is named as EEF. And there's a field resistance REF, and the field coil inductance is LEF. So this is the field circuit, which is not connected to the armature circuit directly because it is separately excited. And then we have the armature. And of course, in the armature, you have armature coil resistance and armature coil inductance, but those are neglected in this derivation process. Okay. If you want to be more precise with the modeling, then you should also include something like this. Okay. You should also include, so the armature circuit, instead of this plain line, it would become something like this. So there will be armature resistance, armature coil inductance, as well as the armature resistance. And then you have some voltage here. So this voltage, of course, from here to here would be your EX in that case. That is the term, that is the actual voltage. Induced voltage is EX. And then once the current flows there, of course, the exciter would be loaded. The load for the exciter is the field coil of the synchronous machine. And then you will get the terminal voltage. So if you consider these two elements in the armature also, then your V, that is the terminal voltage that is actually fed to the synchronous machine field, would be different than this EX. However, for this derivation, they are ignoring that. So we are also ignoring it. So simply whatever voltage is induced is directly available as EX. And that EX is fed to the field circuit of the synchronous machine. So if you apply KVL, for the exciter field circuit first. So simply apply KVL. So the current flowing here is IEF. So simply you can write EF is the voltage source input. There's some drop IEF plus some flux linkage, change in flux linkage, that is d psi over dt, where psi is simply L into I. So d psi over dt would be simply L d I over dt. So that is LEF DIEF over dt. Now, if so, once the field is being excited, so there will be some flux lines out of the field coils due to the current flow, and of course, it has to pass some air gap. You can see there's air gap between the field circuit and the armature circuit. So of course, there will be some leakage. There will be some leakage flux. Not all the flux would be coupled to the armature coils. However, if we can neglect this leakage element, okay, whatever element of leakage flux is there, if we can neglect it, then we can assume that, well, this EX, the output voltage, is again simply the function of the total flux that is produced here, the total flux linkage actually, okay. So we are assuming that none of the flux that is generated by the field coil of the exciter is going away, and that is not coupled actually to the armature coil. So all of the flux are linked with the armature conductors. So if that is the case, then we can simply write EX, that is the output of the exciter, output voltage of the exciter, is KX into psi. We'll look into KX probably later on. Okay. So E is equals to KX into psi. Now, the problem is that, because as we all know that once we start to increase the I, okay, once you start to increase the I, let's say this is my I. Increasing I means you increase IEF or you vary REF, you reduce REF, you reduce the resistance for this path. Then whatever flux you are going to get, the problem is that, well, to start with, because it is separately excited, so there is no need of residual flux. You can even start from the very beginning. So it will start, it will go linearly up to a certain region, and then the problem starts, there is saturation, which is a non-linear phenomena, okay? Up to this point, it is linear, let's say. To this point, it was linear, means it is more or less like Y equals MX. Up to this point, it is Y equals MX. But beyond that, there is saturation of the air gap. And that's why even if you increase the I in the field circuit through the field coils, you are not going to get any additional phi out of it. So this is the nonlinear zone. This is the nonlinear phenomena. So we have to model it, okay? We have to include this effect. We have to express this nonlinearity in our modeling. Okay, so how are we going to model it? Let's see. And besides this, there is another effect. As we know, once you are loading the generator, okay, if I draw the OCC again, this is one thing. Okay, now instead of drawing like I versus phi, I would like to draw I versus E. Okay, so this is IEF, this field current, and the output voltage here is EX. So I would like to draw in terms of the induced EMF, and of course the induced EMF is some function of phi. Okay, so this is OCC, which means it is open circuit characteristics, OCC. And if I draw a line like this, I will get a constant resistance. That is, the slope of this line basically represents a constant resistance lines, because it is E versus E divided by I, which of course would give you a resistance value. So this slope which is tangent to the initial part, to the linear part of the OCC of a DC machine, is known as the constant resistance line. Let's say air gap resistance, we call it RG, R gap, air gap resistance, constant air gap resistance line. Now this is OCC, so this is while your machine is unloaded. Okay, your DC machine is unloaded. But once you start to load it, what would happen? What would happen to this EX? Remember, this is the terminal voltage actually. So if it is unloaded, then of course you are going to get the same voltage over here. But once you are loading it, then what would happen? And of course, the load is varying. So what do you expect to this value of EX? Okay, so now what will happen? Your EX would be affected by some loading. And the loading, in the loading, actually, there are two things. Actually, we are ignoring one part, but let me write the generalized form. So let's say the current here is armature current IA that would flow once the circuit is closed by introducing the load. So let's say this is IRA, where R is the armature resistance. But because as we are neglecting the armature resistance, so that would not be there. But there is another effect or effect, that is armature reaction. You can neglect it. You can't neglect it. So due to the loading, actually your voltage, ultimate voltage would not be EX. Let's say that voltage be E, some voltage V. Sorry, V. So V would be EX minus some drop. Even if we are neglecting this because we are not introducing any RA here in the armature circuit, but there would be some armature reaction. And in the armature reaction, as we know, there are two effects. One is cross magnetization, one is demagnetization. And due to the cross magnetization, the field will be distorted, the main field. And for the demagnetization, actually the main field will be weakened. Okay, it will become weaker. So because of that, actually you will have a reduction in your EX. So you are not going to get the same curve over here, rather you are going to get something less than that. And of course, that reduction will only increase with respect to IF. So this gap would increase as we are increasing I. This gap between these two, the unloaded case, unloaded voltage output, and loading case voltage output, this gap would increase based on the increment in I. So the more increase in I you give to this circuit, the gap would be more pronounced between the unloaded case, the OCC, and the external characteristics. We call it external characteristics of this DC generator. So there are two effects thus. So one is the magnetic saturation effect. That's why voltage cannot go straight like this. And another one is loading effect. That's why we are having some armature reaction effect, even though we are neglecting IR. But in general, there is some IR, armature resistive drop. So if we combine these two effects, the curve that we get, it is called as constant load saturation curve. So the second curve is this one, the constant load saturation curve. Means it is a saturation curve with a constant resistance line. Okay, the same resistance line is there. You are not going to change the air gap resistance. Same field resistance or air gap resistance is there, same gap. So the constant gap or constant resistance line, constant RG. Now the machine is loaded and there is saturation being taken into account. So these three things, constant resistance line, the system is loaded, and there is saturation. So in the second curve over here, you are getting these three things all together. So that's why it's named as the constant load saturation curve for the exciter. And simply it's a DC, separately excited DC generator. So thus we will get two curves. One is the OCC curve, another one is the constant load saturation curve. So with these two curves, let's see how we are going to now get the idea about the modeling. We continue with the modeling. So from the figure now, what we can do, we can see that, well, if we, these are the two curves I just talked about. One is the open circuit curve, another one is the constant resistance load saturation curve. So the open circuit curve is actually only available in unloaded case. So that's why it is in dashed form. But in most general case, your system would be loaded. You are going to apply this voltage, exciter output voltage, to your synchronous machine. And that field circuit is the load for this excitation system, DC exciter. So this is the practical curve that you are going to work with. We are not going to work with this. So this is the constant resistance air gap line RG with the slope over here. Y-axis gives you EX, X-axis gives you IF. And if you choose a point on the OCC, that point is the relation between EX naught and IEF naught. The naught just means it is actually the point corresponding to OCC, or open circuit curve. Okay, it's a point on the OCC. But you're not going to operate there. You are going to operate under loading condition, and your operating point is going to be on the constant resistance load saturation curve, not on the OCC. So thus you are expecting some current different than IEF0. And if this current is any arbitrary IEF, so you can write IEF at this operating point is the summation of this current, that is IEF0, plus any change, this deviation, and that deviation is represented by delta IEF. So IEF is simply IEF0, which is this, plus delta IEF. So this is nothing but your IEF0. So simply we are writing IEF equals to delta IEF plus IEF0, where delta IEF is the nonlinear function of EX. So delta IEF is, again, you see this gap, as I said earlier, this gap would only change if you change your EX. If you are taking EX, why is it called as the function of EX? Let's see. It is of course a function of EX, that's clear, but it is a nonlinear function. Why it's a nonlinear function? Because of its nature. You can see this gap, it's not same, it's not constant, it's increasing. Okay, so if you choose a different EX, if you, instead of choosing EX here, EX not here, or EX here, if you choose EX not here, then that delta EF would be different than the delta EF we have shown over here. If we chose EX not here, then again this nonlinearity is different, this gap is different than the gap presented here. So that's why because this gap is not constant between these two curves, that means it is a nonlinear phenomena on its own. So we call it that we represent this delta IEF as the multiplication of EX and some nonlinear function of EX. Okay, it is a multiplication of EX itself, because if we are changing EX, then delta IEF is going to change, and there is some nonlinearity associated with that, which is again the function of EX itself. So this is the notation used in the literature. Delta IEF is EX multiplied by some nonlinear function of EX. Okay, so now if we want to rewrite EEF that we actually started with in the previous slide, we showed the EEF. So in the first slide of the modeling, here was the EEF. So EEF was nothing but REIE plus D LEF DIEF over DT. So if now we know IEF, okay, we have represented IEF in terms of some incremental variable del IEF plus some terminal voltage EX of the exciter divided by the constant resistance line RG. So we put this relation in the previous expression of EEF. So it was EEF equals REF IEF. So IEF is broken down into two parts. So we simply take into account that. And then the next parts, remember the second part was again, the second part also contained IEF because it would become D, okay, LEF DIEF over DT. So if I put DIEF over DT, so you see IEF DIEF over DT, you will have a DEX over DT term. So this is the DEX over DT. Simply you replace and you should get this expression. Okay, you simply replace the expression of IEF in this previous expression and you simplify, then you should get this. It's nothing special. So once we replace this, then we can see that, well, we have already established a relationship between the input voltage to the exciter, that is EEF, and the output voltage of the exciter, that is EX. And of course, this is in dynamic form. Okay, this is in dynamic form. But still it's a relationship. We are able to relate the output and input directly now. So the intermediate variable IEF is actually taken out of question. So there is the IEF is actually the intermediate variable, which is actually linking this EEF and EX. So what we have done, actually, we have gotten rid of this IEF and we have related and we have got a relationship between EEF and the EX, of course, in dynamic mode. Okay. So now remember our overall representation till now in our synchronous machine modeling, it was done in per unit, okay, per unit form. So again, once again, we started with some actual values of EX and EF and IEF and RG, all these things. So now we are at a point where we would like to introduce the per unitization for exciter model. So what we do, we simply choose some base values first. So the output of the exciter base is the same as the EFD base. This EFD base was required in the synchronous machine modeling part. Okay, remember we had this variable name already available. EFD is already present in our third order model. So whatever base we chose there for per unitization, the same EFD base, exciter field voltage base, is chosen as the exciter EX output voltage here, EX base. So then IEF base, the current in the exciter circuit, field circuit, of course, exciter field circuit is simply the voltage base divided by the resistance RG that is there, the air gap resistance. And RG is simply again RG base. So you can also call it EFD base divided by RG base, all the same. So then per unitizing the exciter output voltage expression, what you have to do, we already have an expression for EEF. So simply you have to divide the whole thing by the related base, corresponding bases. So once we do that, do some simplification, and then we get the representation of EEF now with an overbar. Okay, so this overbar means now these quantities are in per unit. So you have got, after per unitization conversion, we get EEF per unit equals REF over RG multiplied by EX per unit, whole bracket 1 plus, this is the saturation function. The overall saturation function SE is now in per unit, plus 1 upon KX, and this EX over EX base gives you EX per unit, time derivative of that, where this SEEX is a little bit manipulated in this manner. Okay, so SEEX is not straightforward, so you have to do this manipulation assumption. So SEEX is RG SEEX, and that is equals to again delta IEF per unit divided by EX per unit. So if that is done, then
Sir, how is RG calculated from the open circuit characteristic?
It is very easy. Simply take Y upon X.
On the OCC curve, sir, right?
No, it's not calculated from the OCC actually. It is calculated from this air gap line. But it has to be drawn in a manner such that it is tangent to this OCC, the linear part of the OCC. So in a way, this is actually related with a certain OCC. Means if you, let's say, well, how is it related to the OCC? Let's say that. Let's mention that before we proceed. how can we change this OCC for a certain machine? Remember, this is open circuit curve that gives you the idea of the open circuit voltage. Let's say E0 for a DC generator. Okay. What's the relation? The relation is K and phi. Now, I don't know whether you remember this, I mean, old knowledge, which you probably took with me in your 2-1, okay? Probably in 2-1, this
Yes,
machine.
sir. We can do.
So this is your OCC, let's say. If you, let's say, now you are not bothering about phi, okay? You are changing the N. You are not changing phi. You are changing the N of the prime mover so that your generator N is also updated. So if you do that, if you increase N, then your OCC would be something like this. If you decrease N, your OCC would be something like this. So you see, you are changing N, you are getting different E for a certain I, right? If you set your I fixed at a certain point, for the same I, because you are changing N, so you would be able to get 3 different OCCs, and their resistance would be again different. You get the idea? So you see, now you calculate, this is RG, something different than this. You calculate RG, it is something different than both of this.
Yes.
So in this way, actually, this RG is dependent on a certain OCC.
So from this graph, the operating point is not RG, not only RG plus del IF. I mean, there is also some difference between the air gap line and the OCC. I was wondering about that part.
Yeah, that's why it is a function of EX. I mean, that's why the function is a little complicated. It is not simply a function, nonlinear function of SEEX. So that's why you have some additional EX. Okay. This is a very complicated function to explain. It's not straightforward.
Okay.
I mean, you could only simply say, well, there is EX, there is EX. So why are we not writing simply SE as a function of EX? It's not so straightforward. This increment is very complicated expression. And SEEX itself is a complicated expression. We will look at the expression later on. Okay. What you are mentioning is probably this gap, this first gap, right? There are 2 gaps.
Yes, sir. Yes.
So all these are actually taken into account. This second gap, the second gap, delta IF, is actually taken into account in such a manner that the first gap is also being included here, the first effect. Okay. Because if you are choosing a different EX, let's say, if you are choosing a different EX, it means what? It also means you are actually choosing a different EX0, isn't it?
Yes.
Let me clear the figure. It is too hazy now. Although we are saying that, well, I am choosing an operating point here, but this operating point is fixing actually 2 things. First thing, it is fixing some EX0, of course, on this curve. And next thing, it is also fixing some EX. But the EX and EX0 are they different? I mean, if I say this is EX0 corresponding to IEF0, corresponding to IEF0, then I say this is EX corresponding to IEF. IEF and IEF0 are different. That's fine. But you see, EX and EX0, they are not different. They're the same thing, isn't it?
Yes.
So they are same. So it is not a straightforward explanation over here. Okay, it's not straightforward. So in a way, you can also say this is EX0, right? This is EX0.
Yes, sir.
That will take into account this gap also, the gap you are mentioning about. Once you take EX0, then you are actually fixing a different point over here, different EX0, different point here. So the gap is changing. That's why it is function of not only this gap, it is also the function of choosing the first point here. If you choose a different point, you are choosing a different EX0. So does this delta IEF is actually getting affected by these 2 values. So what we are writing actually IEF is delta IEF. What is delta IEF? Delta IEF is this complicated expression. What is the remaining part? It is a function of EX over RG. And what is that? EX over RG. Remember, EX and EX naught are actually same thing. EX and EX naught are not different.
Yes.
They are same thing. So you can also write EX naught over RG for this constant resistance line.
Yes.
Okay. So then, okay, so let's continue with our, okay, so we are talking about the bases and we have covered the bases. So ultimately you get, after some simplification and some manipulated assumption, this SEEX, for this SEEX, we get the per unit representation for this. And once this is done, so later on, we will see probably from the next slide that we are not going to reuse these overbars, but next part of the derivation actually belongs to per unit representation. But we are dropping this overbar notation, okay? But you have to, so from here on, you will see probably, okay, probably in the next slide, you will not see these overbars anymore. In this slide, they are still there. So the per unit saturation function is now represented in terms of two variables, you can say. One is the distance. These are the two distances. Okay, one is the distance of this A, that is the distance. That means it is simply, you can say this is what? This is IEF, but in per unit now. And this is your IEF naught. And the saturation function is nothing but, you can say it is some relation between these two distances. Okay. So if you change EX, that means it is still a function of EX, per unit EX. So now it is EX per unit. This is IF per unit. Still they are EX and IF, but in per unit. So the relation is established by these distances alone. This A minus B. So A minus B means what? This is delta IEF. So A minus B would simply give you delta IEF divided by B. What is B? B is your EX or IEF, sorry, IF0. This distance is IF0 belonging to this point. So with the help of this, you can represent the saturation function in per unit. Okay, the per unit saturation function is represented in this form. Now the parameter Kx, as I mentioned earlier, we have to also deal with the Kx. We didn't mention too much about Kx there. We simply wrote Ex is some function of some, we can also call it some like machine constant. Okay, Ex is some machine constant multiplied by the psi. Because the psi, if you remember why this Kx is a machine constant, if you remember, E is in general the no load EMF. The no load EMF is in general represented like K and phi, right? Now, what is N phi? N multiplied by phi. Okay, if you go to the Faraday's law of electromagnetic induction, okay, let's go there. What is E induced? The Faraday's law.
So N d phi by dt.
N d phi by dt. Excellent. So now N phi, can we write it like this? Because N is a constant.
Yes.
Now, can we write it like this? So N phi is nothing but the flux linkage. Okay. So you see the flux linkage is psi, which is N phi, and psi is also Li. So we can also write L di over dt, isn't it? The same Faraday's law could also be, or the voltage induced expression, you could use N d phi over dt, or even you could use L di by dt. That is actually the current flowing through an inductor or a coil. Whatever voltage is induced in that coil, that is the expression for that. So both are actually being used. So you can also write this like dLi by dt, where Li is your psi. So in a sense, we can say this psi is actually similar like N phi. Okay, this N phi over here. So if we remove that now, so we are left with Kx. So this Kx is actually the machine constant. And because in the DC machine, that depends on, like, say, your parallel path, number of poles, all those things. Okay, number of conductors, Pz over 60A. Probably it is something like that. Pz over 60A. Yeah. So this is the expression of your Kx here. Okay, so now if we try to manipulate Kx a little bit more in terms of some known quantities or some per unit quantities, then we'll continue in this manner, that Kx is equal to Ex over psi. So Ex was Kx into psi, so simply take Kx equals Ex over psi. Sorry, Ex equal to Kx into psi. So Kx is now Ex over psi, and psi is Leif, and then you replace Ex, Lef, Ief. So now you convert Ex and Ief into their corresponding per unit representation, and thus an additional Rg arrives there. These are not in per unit, but these two are in per unit. So when you per unitize, you have this additional Rg over here. Okay. So what you have to do, you have to simply take the base values, corresponding base values. What is the Ex base? Ex base is EFD base. What is IF base? You see there is an additional Rg. Okay. So when you divide Ex base and IEF base, you get an additional Rg. So this is the additional Rg over here. When you take the per unitization for these two, and Lef remains there. Now for any given operating point, that is IEF0 and Ex0, we let some inductance expression, that is L field, but in unsaturated form. So LFU is the unsaturated inductance, okay, at a certain operating point. And that is assumed to be equal to the actual inductance LEF multiplied by this factor IEF0 over EEF0. So if we can assume this, okay, then we would be able to simplify the expression of Kx in this manner. So Kx is now Rg over LFU. So what we have simply done, we have simply gotten rid of these three. Okay, simply in terms of the unsaturated inductance and the actual inductance based on the operating point information. So this is the operating point information. So if the operating point information changes, of course, your unsaturated inductance will also change. So why it is actually changing? Because you see the field inductance is actually a function of the field flux linkage. Okay. So because your flux value is actually a function of current, number one. Second thing, this distance is actually increasing even before saturation. Even before saturation, this distance is increasing. The complete saturation occurs probably somewhere here. So this gap is actually changing depending on your operating point selection. So that's why the unsaturated field coil inductance is also a function of this operating point itself. Okay. And if we can do that, ultimately what is the benefit? The benefit is that Kx could now be represented in a simpler form, that is Rg divided by LF unsaturated. And then we get Okay, then we rewrite the EEF expression, this last EEF expression. And now we change this KX, we replace this KX by whatever we have got here, and that is LFU over RG. Okay, so you replace the KX by LFU over RG and you call it TE. So you see it was 1 upon KX over here. So that means whatever KX is there, it would be inverted. So LFU over RG would be there. But we have again taken it equals to TE, some time constant. Remember, in an RL circuit, what is the time constant? RL series circuit.
L by R.
L by R. So this is some form of time constant. That's why we are calling it exciter time constant. Okay, exciter time constant TE. Okay, then we are left with the remaining part are actually the KEEX plus EX, probably the same. So yeah, REF over RG is there. So REF over RG, you see the first term is actually taken as the KE, that is the gain, that is the ratio of two resistance elements. One is the actual field resistance, another one is the air gap resistance. So this ratio is translated as some gain value. Okay, that is the KE exciter gain, and the middle one is probably, okay, the middle one you have just opened the bracket, so that's why you have two different elements there, the first element, the second element, and the third element. Second element remains as it is, that is EX multiplied by SEEX and in per unit. And then okay, so this SEEX and this SEEX over here are not same. So remember, we have REF over RG into EX per unit multiplied by S small e small SE function of EX per unit. So there is an additional REF over RG with this small SE, which is not here because we have again taken some more simplification, actually nothing else. So this S capital EEX is now have also taken into account this ratio REF over RG. Or you can simply say this is KE SEEX equals to S capital EEX. So you don't see REF over RG here. Okay, so there's a small change in the notation here. This is S capital E. The previous one was S small e. So now it seems that we have got a pretty cool relationship between our input voltage for the field and the output voltage for the exciter armature. And then we should be able now to represent it in block diagram form. Okay, so what we can do for that, we can copy this probably. No, here. Oh, it is already there. Okay. So what is done actually? There is a mistake. There is a mistake. So you see, if I take DEX over DT, then this thing should go to the other side with the minus sign, and this second term should go to the other side with the minus sign. So probably I did a mistake while typing. So this should be minus. I will correct it, inshallah. So this is not plus. This is a minus. Okay, only this EEF will remain as plus. So now this is actually represented in this form. So you have got a block diagram representation, which looks like a transfer function representation, but it is not actually a transfer function representation because there is still some non-linearity. This is not linear. This is non-linear function. So it is not a pure transfer function. It's not a linear relationship, but we can at least we can say that, well, it is a block diagram representation, okay, with some non-linearity present in it. However, if we can get rid of this non-linearity, if we can approximate this with some linear function, then the whole thing would become a transfer function. Okay. So how to get this out of this? It's pretty simple. Okay, there's a minus, remember. So what we are doing, we are simply adding We're simply adding KEEX. So KE is the gain. So K is the gain. What is the input to the gain block? EX is the, so EX is the input to this gain block. So here we are getting KEEX. Then what we have another EX getting multiplied with some function, saturation function, of course in per unit. And this is again some nonlinear function. We'll look into it later on, how to deal with that. So SEX, it takes input EX and gives you the output of this multiplication. So here this is, we are calling it as VX. So this block is nothing but VX. And this is the VX we are writing over here. At this node, we have VX. So KEX is done. And remember, this is minus in between. So actually we are adding them. We can simply add these two blocks and we can put a common minus sign there. So this is the addition. This is the summing junction. And once the sum is produced, then we have a minus sign. Minus with what? Minus with the input to the system, EEF. EF, remember, is the input. So this is EEF, which is coming with a plus sign over here. This is plus. So plus and minus, you get the signal back. Then this is DEX over DT. How do you write it? If you take Laplace transform for this part, then you can easily write it like S TE into EX. Okay. So then you have the additional STE. So this additional STE would become now, if you take only EX on this side, then you can write EX alone is actually 1 upon STE. 1 upon STE multiplied by the whole thing that is already there on the right hand side. Okay. So the whole thing on the right hand side we have already got at this node, that is EEF minus the summation of these two, then negation, and then you multiply this, the whole thing, with 1 upon STE block, then you would get EEX. So that is your EX. So this is how we actually get it. So this is the explanation for block diagram. So once this is done, then this is actually the model for the DC exciter. However, still we have one nonlinearity present in terms of saturation function S capital E. So to get rid of this nonlinearity, in the what they do actually, they assume some expression or some representation of this this SEEX or this VX actually overall, because VX takes into account the EX multiplied by SEEX, the whole thing. So the whole thing, the EX multiplied by SEEX, is approximated or represented by this exponential relation with some constant AEX and some other constant BEX and the exponential relation itself for EX. Okay. There are, of course, some other representation for VX. So most commonly used is this, okay, which is of course a nonlinear function. You see the presence of exponent here makes it a purely nonlinear function. And of course, from our curve also we saw that, well, it looks like an exponent, right? So it's pretty logical to include some exponential relationship here to represent this nonlinearity of saturation function, or dependence of saturation on the operating point EX. So it's represented by some exponential function. And once we can do that, then simply we can take the linearized form. So if we linearize this, what should we get? If you simply write Vx equals del Vx plus Vx0, then that should be equal to what? AEX. Remember, I told AEX is a constant. E to the power BEX. BEX is another constant. Then you write EX equals EX0 plus del EX. Okay. Then you simplify this. You simplify these exponents, and simply you take the Vx naught from both sides. Vx naught should be equal to AEX e to the power BEX into EX naught. If you can take it out, then whatever would be left, you should be satisfied with that. Another way to do that is simply apply the Taylor series expansion. Okay. Taylor series expansion, and simply take the first order term. Okay, don't go for the square terms and truncate the higher order terms. You can get it. Okay. So that by that I mean actually this. So you take, you calculate di Vx over di x, di Ex, and you evaluate it at Ex naught. Okay. This because this is the operating point. You evaluate it at Ex naught, and by the variable change in variable. So that is del Ex. So that would give you the linearized version of this right hand side. And then you can get the linearized representation for this. So once you can once you are able to linearize it, then you can replace this nonlinear block by that corresponding linear expression, and then purely that would become a transfer function representation. But before that, there are a few things to be mentioned. One thing is that here the input voltage is what? Input voltage is EEF. Now the question is, from where actually this input voltage is coming from? So for knowing that, if we go back to our block diagram, the big block diagram, this is the input to the exciter. Remember, this is the exciter representation, DC exciter. So we have to talk about what is the input, from where is the input coming, and where the output is actually going. So if you see, this is the exciter. The input to the exciter is coming from where? It's from the voltage regulator. So this is, we are calling it simply VR. So this is my voltage regulator output VR, which is actually driving the exciter circuit. And the output of the exciter is simply, we call it EX, but we see here that that is actually being fed to the generator field. So simply we can write it as EFD. Okay. So the input is EEF, that is actually coming from the regulator in the big picture, from the big picture. And the output, which is EX, that is actually going to the generator field. So instead of writing like EEF and EX, we may also use VR and EFD. Okay. Now another remark is this, that if this REF is varied, okay, REF. What is the REF? REF is the field resistance, field circuit resistance. This is a physical resistance. It is not the air gap resistance, the physical resistance. So if the field resistance of the REF is varied, from the relationship, we can easily justify this. We can easily verify this, that KE is affected due to the change in REF. That is the gain that we assumed here. You see, it will be affected. If we change REF, KE will be affected. If we change REF, my saturation function here would be affected. However, the time constant remains unaffected. Okay, because time constant is not a function of REF, it is a function of the air gap resistance and the unsaturated field inductance. Okay, so now because it looks, I mean, we can easily simplify this. Okay, we can easily simplify this. There are two, there's a feedback path. In the feedback path, we have two blocks which are working in parallel. So we can simply add them. Of course, after this is being linearized, okay, after this is being linearized, then we simply add them. The linear, this is already in linear form, this is in non-linear form. So you linearize this, you simply add these two, and you apply the negative feedback formula for block diagram reduction. So what I'm talking about is this. Yeah, we are simply looking at the block diagram reduction technique for this overall thing. Okay. After this is being linearized. So once we do that, sorry, we have got, okay, here. So once we do that, then we are actually here. Okay. So that means we are actually looking for a simpler representation or a standard representation and in linearized form. So for that, what we have to do, we have to linearize it as I mentioned, just mentioned. So you go for the linearization and you set an operating point, because for getting a linearized form, of course, you have to choose a certain operating point. So this is the operating point. And then for this representation, you are looking for the expression of K and T. So the K and T, if you go through the derivation, if you take the linearization first, if you perform the linearization for this part, and then if you simplify this block, applying block diagram reduction techniques, series parallel connections, and negative feedbacks, all those things, then you will come up with this expression of K over here and the expression of T over here. Okay, where SEEFD0, you see now this SE, okay, SE is now calculated at a certain operating point because of the linearization. Okay, now SEEFD is a certain value. It's no more a variable. Okay, here SEEX, it's a variable. It is a function of this EX. Okay, but here after linearization, the benefit is that you are actually getting this SE at a certain operating point. So once you fix your operating point, irrespective of what happens to the original EFD, actual EFD, this is not going to be changed, because AEX is a constant, BEX is another constant, modeling constant actually. Then if you fix EFD naught, then you have actually fixed the overall saturation function for a certain operating point. So this SEFD becomes a constant, BX, KE, these are constants. So K and T, they also become constants. So you see now the variable representations are also updated. They are no more in their non-linear form. They have been taken in the linearized form. Okay, so now we have delta EF equals delta VR on the input side, and on the output side, we have delta EX equals to delta EFD. And you see, finally, we come up with a very simple representation with a single block for representing the separately excited DC exciter. Okay. Any question till now? Okay. If not, then let's proceed a little bit. Actually, this is almost the same thing that we discussed earlier here, but in a little. So this was the first picture that we came up with the schematic of excitation system description. Here we only mentioned this limiter and protective circuits, and here actually it is a little bit more elaborated. So you see now this is the generator. Generator provides you the P, Q, and VT. That VT, because it is excitation system, so we are interested in VT. Extracting the information of VT is obtained here by some sensor. And as we all know that we discussed about the load compensation. So you sense it. If there is load compensation required, then you apply the load compensation, and then you send the voltage signal to your AC voltage regulator. Okay. And the AC voltage regulator, you directly feed your AC voltage. Okay. So that is the output terminal voltage actually. The same signal could also be fed back to your AC voltage regulator with the help of the power system stabilizer, through power system stabilizer block, which is actually a one sort of controller, we can say, a supplementary controller. We'll take the detail of it later on, inshallah. Then there are some blocks whose locations are variable. Okay, so those are marked with different number of stars. So the single star, you see the field shorting. The field shorting is a certain block which is only applicable to AC exciter and static exciter. Okay, it's not applicable for DC exciter. Then we have the voltage sensing for the, so there was a voltage sensing for the AC voltage sensor. And there is another voltage sensing, which is actually coming in the feedback path for the DC regulator control. Okay, so you see this is the feedback path. So this is the closed loop through the voltage sensing. So because this is the input to the voltage regulator, so the DC voltage regulator should take the DC voltage, and the DC voltage working here is actually the exciter output. Whatever kind of exciter it is, be it static exciter or AC exciter or DC exciter, ultimately you are going to feed DC voltage to your generator field. So that's why the DC field voltage should be fed to the DC voltage regulator, and this is the voltage that should be controlled by the DC regulator. Okay, whereas the AC regulator doesn't take that field voltage output, rather it takes the exciter voltage output. Rather, the AC regulator takes the AC voltage output directly from the generator terminal. So the AC regulator controls directly, it has control directly over the variable of interest, that is VT. Whereas the DC voltage regulator, it only can control the field excitation. Okay, the DC one, not the AC one. And these are the references. You can change the reference points if needed. And based on these reference values, actually the DC regulator or the AC regulator will work. It will calculate the error, and the error would be fed to its internal control circuitry, and accordingly the signal would be fed to the excitation field circuit. So this is actually your VR. We talked about VR. Remember, this is the VR. So the VR would be obtained from the output terminal of the DC regulator or the AC regulator, whichever is working. And this is your EFD. The exciter is providing the EFD. So these are the locations. And the double star means that these voltage sensing here, it is shown as a closed loop control. However, in some system, it could also be open loop. Okay, that is manual. Here it is automatic, but it could also be manual. So this is second one. First one, I said the field shorting circuit. It is needed just to discharge the energy in case you are shutting down your generator. Then whatever energy is stored in the field, you have to discharge it. So in those cases, the field shorting is required. Well, then what is left? Okay, these limiters are left. Oh, besides that, we also have an excitation system stabilizer circuit. Probably the detail of this we will take in the next lecture. So we'll leave it for the time being, and we take the remaining three. So over excitation limiter, under excitation limiter, and volt per hertz limiter and protection. What is the problem of over excitation? Can anyone mention? Let's say you have the rotor core for synchronous machine. This is the field coil. Then you know what is the excitation, maximum excitation current I, let's say I exciter. You know the limit for that. However, that I exciter has gone beyond its rated value. So what would be the problem? Let's say there's some value I exciter rated, and at a certain condition, certain point of your operation of your generator, you are getting this I excitation greater than I exciter rated. What would be the problem?
Sir, exciter field coils will be damaged.
Yeah, that is one thing. Anything else?
Sir, terminal voltage will be very high.
Yeah, that is also true. Anything else? So, okay, terminal voltage would be high. This is questionable. I will explain that why it is questionable. Terminal voltage would be high. The first thing is okay. This coil would be, let's say, carrying overcurrent, and if it carries overcurrent beyond its rated value, of course, it will be heated, right? So the field coil heating will occur. So heat generated in the field coil. That is the problem. Terminal voltage would not be more beyond a certain value. Because of what? Because of saturation. Remember?
Yes, yes.
There is saturation. So if this happens, probably there will be saturation. Flux would be saturated. If flux gets saturated, remember your generator, and ultimately it would be also connected to the transformer. Okay, so the saturation is a bad thing for the core of the machine. Why? Now the core itself would be becoming heated, increased eddy current loss and hysteresis loss. Remember, eddy and hysteresis, these two will come into picture. So of course, the eddy would be much more pronounced because hysteresis is depends on the frequency. Okay, if frequency changes, then hysteresis gets affected more. The eddy is actually the criminal for causing heating of the core. So if your core gets saturated and even then you are providing more and more current, the problem is that you are not going to get any additional voltage beyond a saturation point, but your core would become saturated and that would create core heating. So this heating is the field coil. First of all, the field coil would be heated and the rotor core, this rotor core would be heated. Okay. So that's why you have to limit the overexcitation. You have to control the overexcitation. You shouldn't allow it. So there is a limiter. Okay, there is a limiter associated with that. And okay, the third 3 stars were missed. The 3-star means, okay, there's a comment. So this also, here it is actually connected to your AC regulator, but this could also be connected to the DC regulator. I'm mentioning about the DC regulator part. Okay, that here it is connected to the AC regulator part. Ultimately, both regulators are actually controlling your field circuit. So it doesn't matter whether you place it here or you place it in this loop. Okay, ultimately this signal is driving your exciter circuit. So ultimately your this field coil heating and your field coil saturation, your core heating, rotor core heating, all are going to be there irrespective of the location of this block, be it in the AC regulator loop or be it in the DC regulator loop. So there is a chance that this could also be in the DC regulator loop. Okay, then what else? Okay, so under excitation. What is the problem for under excitation? Over excitation is understood quite easily. Again, the under excitation, it has to be understood actually from the capability curve. So I hope that you did take it in your energy conversion 2 course, those who are from IoT background. So from the capability curve, it is observed that if you go to that, then under excitation, if you provide under excitation, and that is yeah, that, so there are 2 things. One is under excitation, and also at the same time, if your machine is running in excitation, leading power factor operation. So if these 2 things combines, then it is very much detrimental for the stability of your system. Okay, so this thing could easily be understood from the, so leading power factor operation and under excitation. If these 2 things happen at the same time, then it is detrimental to your stability of your synchronous machine. Okay, you can easily get the idea from the capability curve. Volt per hertz limiter. What is the problem with that? The last one, I will take probably 1 or 2 minutes. Volt per hertz limiter, that means V. So we are relating V and F. What is the relation between V and F? Let's try to figure it out first. Again, V is equal to V or E, whatever, the induced voltage or the terminal voltage, it is K and phi, right? Or instead of N, we can also write K phi omega, angular velocity omega. Omega is related with frequency. How? Omega is related with frequency like this, 2 pi f. Okay. So the problem is that we're talking about V by F ratio, right? So V by F is actually some proportional to phi, isn't it? So if you don't make it a constant, then what would be the problem? Or if you don't limit this ratio. So you see the relation now, V by F, volt per hertz limiter. If you don't limit this ratio to a certain value, then your phi will be affected, isn't it? And we all know if phi is affected, then either overexcitation will happen or underexcitation will happen, right? So this is why this rate is actually indirectly affects your excitation of your system. It actually affects the phi. If phi gets affected, your core gets saturated if it is in the overexcitation mode. If it is in the underexcitation mode, if this thing happens, then you are in the unstable zone. You are in a danger of moving into the unstable mode of operation. So in both cases, it is a trouble. So you have to limit it. This ratio has to be limited. Okay. So these are the limiters. And of course, in any case, any of these limits are violated due to the failure of your limiter circuit. Okay. Limiter circuit might not be operative. If it is not operating, then as a backup plan, you have to keep your protection device active. Okay. So associated with all these limiters, you should have some protection. Backup plan. If limiter works, then protection is not required. If limiter doesn't work, protection is required. The one thing is left, that is excitation system stabilizer. It has a certain job and it has a modeling part. So we will look into it in the next class, inshallah. We have one more week before our mid exam. So probably next week will be the last week before mid exam. Okay. So after that, you will sit for the mid exam, and probably our secretary, Mr. Faisal, probably would communicate with you guys for setting the dates for your exams. Okay. So accordingly, please help him in filling up the blanks, the dates for your courses. Okay. So when you set the dates, because now the courses are different for each of you probably. Okay. Some of you probably have taken 2 courses, some of you probably have taken 3 courses, and so on. And some of the courses might not match even. So while you set the dates, please look at others' comfort also. Okay. Don't set the dates according to, your own comfort. Okay. Please leave gaps for others so that they can also fill up the blank space, keeping some gap in between. Okay, so thank you very much once again, and inshallah we will meet in the next class in the next week. Okay.
Excuse me, sir.
Yes.
Mister, how do you set your questions?
How do I set my question?
Yes.
Okay, if you have time, but probably not everyone is here. The question will be, you can take example from the previous year's questions. There will
So
be.
where can we get the previous
Okay,
questions?
I may share that with you. I may share that with you. But generally,
Yes, sir.
in the previous years, I took it in open book type, open book exam. This year, I don't know whether I will go for open book or closed book, because when it becomes open book, then it is difficult to set the derivation type questions in the exam because everything is available to you. Probably I will still go for open book exam just for your comfort, so that you don't have to memorize everything, but just you have to focus on understanding the things. Okay. So once it becomes open book, then no problem. You just try to clear your concepts. Then whatever comes, whatever is the question type, it doesn't matter. Okay. So that you don't have to memorize anything. This is the very short suggestion for the exam. There will be 3 questions and all the questions should be answered. There will be no options. And the time would be probably maximum 1.5 hours. Anything less than that is also a possibility. Okay, there could be all like probably no derivations would be there, or the derivations would be, if there are any derivations, then that would be from those part which I didn't cover in detail in the class. Okay, so probably I just said, okay, do it on your own. So just for checking whether you did it on your own, then I may just for checking, I may give you some small derivation. Other than that, mostly conceptual questions, and if there are some mathematical expressions, then associated maths will also be there. MATLAB coding could also be is also a possibility. Okay, so you have to write the code and you have to submit the main file, M file, along with your script. Okay, So you have to code it in MATLAB. In that case, you don't have to write it in your script. You just code it, and just you, in the place of answer, you just mention that, well, this M file with this name has been attached with the answer script. Okay, that would suffice. I think I have told everything associated with the exam. Is
So
it
if
okay?
the exam is in weekdays, it will take place at night, right?
Actually, I don't know this. So you have to consult. Probably the options will be given. I don't know actually which dates are available for your exam. Okay. So is there any group where Mr. Faisal is also a member for the postgraduate students? Didza, you are an old citizen here. So is there any group?
Yes, there was a group, Facebook group.
Okay, so I think the group is still active, and usually what happens is that in that group, actually these things are being discussed and finalized, as far as I know. Okay, who are there other than you? Anyone else? Very small number of participants. Anyone else from IUT background? Okay, Rahid is there. So Rahid, how actually you finalized your dates for exams? Hasanudjaman Rahid, probably he has left, but is showing to be there. Anyone else who took course earlier? No, I don't think so. Others are either from non-IUT background or new to the MSc course. Okay. Okay, I will talk to Mr. Faisal, okay? And probably I will give you some update in the next class, inshallah. Okay then, so see you in the next class. Okay, assalamu alaikum.